Is our universe all there is? Or is it just one of many, floating in an unfathomably vast sea of realities, some eerily similar to ours, others governed by entirely different laws of physics? The multiverse theory, once relegated to the realm of science fiction and philosophical speculation, has surged into scientific discourse over the last century. It poses a question as profound as it is unsettling. What if everything we've ever known is merely a tiny bubble in a grand cosmic foam? The idea of a multiverse offers a radical reimagining of reality. It doesn't merely expand our universe, it shatters its borders entirely. This concept challenges the finality of existence, suggesting that our cosmos might not be the singular stage of creation but part of a much grander, possibly infinite structure. From theoretical physics and cosmology to quantum mechanics and string theory, the multiverse has emerged as both an explanatory model and a subject of deep controversy. Chapter 1: Ancient Echoes, Philosophical and Historical Origins. Long before telescopes pierced the heavens and equations mapped spacetime, human beings pondered the infinite. In ancient cultures and philosophical traditions, the seeds of multiverse thinking were already being sown. 1. Early multiverse-like ideas in philosophy. In the 5th century BCE, the Greek philosopher Anaximander spoke of innumerable worlds, rising and perishing in an eternal cycle. Later, the atomists Leucippus and Democritus posited that infinite worlds, composed of atoms moving through the void, could exist independently of one another. These were not just poetic musings, they were early attempts to use reason to explore the infinite nature of being. Centuries later, Roman philosopher Lucretius echoed these ideas in his epic poem De Rerum Natura, On the Nature of Things, writing of countless worlds arising from the random collisions of atoms. Though devoid of scientific grounding as we understand it today, these ancient thinkers were wrestling with questions remarkably similar to those posed by modern cosmologists. 2. Theological and metaphysical interpretations. In many religious and metaphysical traditions, the multiverse finds symbolic parallels. Hindu cosmology speaks of cyclical universes, constantly forming and dissolving, governed by divine forces. In Buddhism, the concept of trichiliacosm refers to thousands of coexisting world systems, each with its own sentient beings and karmic cycles. In medieval Europe, theological resistance to plurality of worlds was strong, but thinkers like Giordano Bruno dared to speculate otherwise. Bruno, drawing from Copernican revolution, argued for an infinite cosmos filled with countless inhabited worlds, a view that cost him his life at the stake, though vindicated in spirit by modern astronomy. 3. The birth of the scientific universe. The shift from speculative metaphysics to empirical science began with figures like Galileo, Newton, and eventually Einstein. With Newton's gravitational laws, the universe became a predictable, mechanistic system. However, it was Einstein's general theory of relativity that would eventually pave the way for multiverse cosmologies. By introducing a dynamic view of spacetime and its interaction with mass and energy, Einstein laid the groundwork for a new understanding of the cosmos. Yet it wasn't until the advent of quantum mechanics and inflationary cosmology in the 20th century that the multiverse concept began to take scientific shape. Chapter 2: Scientific Foundations of the Multiverse. To understand the multiverse as a scientific theory, we must first trace its roots in the most transformative discoveries of 20th century physics. From the strange behavior of quantum particles to the expanding fabric of spacetime itself, modern physics has revealed a universe far more complex and counterintuitive than our everyday experience suggests. These revelations have naturally given rise to the possibility that our universe is not alone. 1. Cosmic inflation, the Great Expansion. In the early 1980s, a major breakthrough reshaped our view of the universe's infancy, the theory of cosmic inflation. Proposed by physicist Alan Guth, inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion. It grew faster than the speed of light, smoothing out space and creating the large-scale uniformity we observe in the cosmic microwave background. But inflation has a peculiar consequence. In many models, it doesn't stop everywhere at once. Instead, while inflation ends in some regions, it continues in others, potentially forever. This is known as eternal inflation, and it leads directly to a multiverse. In eternal inflation, the universe becomes a vast, ever-growing patchwork of bubble universes. Each bubble could form its own distinct universe with unique physical constants, particle types, and laws. Our observable universe would be just one such bubble in an infinite cosmic froth. 2. Quantum mechanics and the many worlds interpretation. Quantum mechanics, the science of the very small, also gives rise to multiverse thinking. At its core lies the principle of superposition, the idea that particles can exist in multiple states at once until observed. But what happens when a quantum system is measured? One solution, the Copenhagen interpretation, says the wave function collapses into a single outcome. But an alternative, more radical idea, the many worlds interpretation, MWI, developed by Hugh Everett III in 1957, suggests something far more astonishing. Every possible outcome of a quantum measurement actually occurs, but in different branches of reality. According to MWI, the universe splits into multiple, parallel realities with every quantum decision. Each version of you exists in a different branch, living out a different consequence of each possible choice, from the trivial to the life-altering. This generates an incomprehensible number of diverging worlds, each as real as the one you inhabit. While it lacks direct empirical evidence, the MWI has gained popularity among physicists for resolving certain quantum paradoxes without requiring wave function collapse or observer-centric effects. 3. String theory and the landscape of possibilities. Another source of multiverse theory comes from string theory, a highly mathematical framework seeking to unify all known physical forces. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings. Different vibrational modes correspond to different particles. To function, string theory requires extra dimensions, up to 10 or 11 total. These extra dimensions are believed to be compactified into tiny geometric shapes called Calabi-Yau manifolds. But here lies the key: there are an astronomical number of ways these extra dimensions can be compactified, each resulting in different physical laws. This leads to what theorists call the string landscape, a vast configuration space of possible universes, perhaps 10 to the power of 500 or more, each corresponding to a unique way the extra dimensions are folded. These universes may vary not just in constants or particles, but in the number of forces, dimensionality, or even the presence of time. The landscape, combined with eternal inflation, suggests that each pocket of the inflating universe might settle into one of these configurations, giving rise to a string-theoretic multiverse. 4. The anthropic principle and fine-tuning. The apparent fine-tuning of the universe. The precise values of physical constants that allow for the existence of matter, stars, planets, and life, has puzzled scientists and philosophers for decades. For instance, if the strength of gravity or the charge of the electron were even slightly different, complex structures like atoms or galaxies might not exist. One explanation is that these values are not unique, but random outcomes in a vast ensemble of universes. This brings us to the anthropic principle. We observe this particular universe because it allows observers like us to exist. In a multiverse context, this isn't just philosophical speculation, it becomes a selection effect. Out of countless universes, we inhabit one of the few where the conditions are just right. The anthropic principle is controversial, but it provides a potential explanation for why the universe appears so uncannily suited to life. 5. The role of mathematics and symmetry. Underlying much of modern theoretical physics is a deep belief in symmetry and mathematical elegance. From Einstein's equations to quantum field theory, the universe's behavior appears to follow deeply symmetrical laws. The multiverse may simply be the natural consequence of this mathematical structure. If the equations permit multiple solutions, multiple types of universes, then perhaps all of them exist in a grand mathematical structure we call reality. This is the essence of the mathematical universe hypothesis, proposed by physicist Max Tegmark, which we'll explore in a later chapter. Chapter 3, Levels of the Multiverse, Max Tegmark's four-tiered framework. One of the most structured and widely cited models of the multiverse comes from physicist Max Tegmark, who proposed that there are four distinct levels of multiverse, each progressively more speculative yet rooted in established or emerging science. This framework provides a useful lens for understanding the many ways in which the term multiverse is used across disciplines. 1. Level 1, Regions beyond our cosmic horizon. The most grounded form of the multiverse is Level 1, which arises directly from standard cosmological theory. It proposes that the universe is spatially infinite, or at least so vast that we can only ever observe a tiny fraction of it. The observable universe, defined by the cosmic microwave background, CMB. And the speed of light, represents just a small patch of a much larger whole. If the laws of physics are the same throughout this larger space, then there are regions far beyond what we can see that contain different configurations of matter. Given enough volume, every possible arrangement of particles must eventually repeat. In fact, it is statistically inevitable that there are other regions, possibly billions of light-years away, where entire galaxies, solar systems, and even near-duplicate versions of ourselves exist. These are not alternate realities in a metaphysical sense, they are simply distant regions of the same physical space, governed by the same laws but featuring different cosmic outcomes due to the randomness of initial conditions. Scientific basis: inflationary cosmology suggests that space is flat and infinite. The observable universe is limited only by the age of the universe and the speed of light. Statistical mechanics implies repetition of patterns in an infinite domain. Implications: our copy may be out there, living a similar life. The vastness of space becomes the generator of multiplicity. 2. Level 2, Universes with different physical constants. Level 2 multiverses emerge from the theory of eternal inflation. In this view, as inflation proceeds eternally in some parts of space, it ends in isolated bubbles, each forming its own universe with potentially different fundamental constants, particle masses, and even numbers of dimensions. These bubble universes are causally disconnected from one another, meaning we could never reach them or receive signals from them. Yet they all emerge from the same overarching inflating spacetime. What makes Level 2 so intriguing is its compatibility with string theory's landscape, a mathematical framework that predicts a vast number of possible vacuum states, each corresponding to a different set of physical laws. As different regions of the inflating cosmos fall into different vacuum states, they form distinct universes, each with its own rules. Scientific basis: eternal inflation and the string landscape. Differences in symmetry breaking or dimensional compactification. Implications: universes may have different chemistry, gravity, or even time structures. The anthropic principle gains traction. We find ourselves in a universe conducive to life. 3. Level 3, the quantum many worlds. Level 3 is derived from quantum mechanics, specifically the many worlds interpretation, MWI. In this model, every quantum event with multiple outcomes causes the universe to branch into several non-communicating realities, each embodying a different result. For instance, in a quantum experiment where a particle can go left or right, the universe splits. In one, the particle goes left, in another, it goes right. Both outcomes occur, but in different branches of the multiverse. This implies that every possible history and future of the universe is playing out in some branch of the quantum tree. The number of branches grows exponentially with time, leading to an unimaginably vast collection of parallel worlds. What distinguishes Level 3 from Level 1 and 2 is that it doesn't require additional space or physical constants. It exists in the structure of quantum probability and wave function evolution. Scientific basis: quantum superposition and decoherence. Unitary evolution of the wave function. Implications: all versions of U that could exist do exist somewhere in the quantum branches. questions of free will and identity take on new meaning. 4. Level 4, the ultimate ensemble, mathematical universes. Level 4 is the most radical of all multiverse types. Tegmark's mathematical universe hypothesis suggests that all structures that can be described mathematically actually exist. According to this view, physical reality is not just described by mathematics, it is mathematics. Every consistent mathematical structure corresponds to a real universe with its own internal logic and inhabitants. Ours is just one such structure. This view implies a truly infinite multiverse, not just in size, but in the types of existence it includes. Universes with entirely different physical laws, logical principles, or dimensionality could all be real within this mathematical ensemble. Scientific basis, philosophical extrapolation of mathematical Platonism. The observation that our universe follows precise mathematical laws. Implications: reality is a subset of all logically possible systems. There may be universes completely alien to our understanding. 5. Comparing the levels. Level key idea mechanism variation Level 1 infinite space beyond the observable universe inflation and standard cosmology initial conditions Level 2 bubble universes with different constants eternal inflation and string landscape physical laws Level 3 quantum branching many worlds interpretation outcomes of quantum events Level 4 all mathematically possible universes mathematical structure. Everything conceivable each level of the multiverse builds upon the prior, requiring greater assumptions but offering broader explanatory power. Whether one accepts all or only the first few levels often depends on one's interpretation of quantum mechanics, string theory, and the philosophy of science. Each level of the multiverse builds upon the last, increasing in complexity and philosophical depth. Level 1 refers to regions of space beyond our observable universe, where the laws of physics remain the same, but the initial conditions differ, leading to variations in how matter and galaxies are distributed. Level 2 takes a step further, introducing bubble universes formed through eternal inflation, where fundamental constants, particle types, and even dimensional structures may differ due to distinct symmetry breakings or vacuum states. Level 3 stems from the many worlds interpretation of quantum mechanics, suggesting that every possible outcome of a quantum event actually occurs in a separate, branching reality. These worlds are not spatially distant but exist in a superposed, parallel quantum structure. Finally, Level 4 encompasses the most expansive idea, that all mathematically consistent structures represent real, physical universes. In this view, any conceivable universe that can be described with mathematics is as real as our own. This hierarchy presents an increasingly bold portrait of reality, starting with distant galaxies and ending with entirely alien realms of mathematical existence. Chapter 4: Evidence and Arguments for the Multiverse. The multiverse, by its very nature, presents an immense challenge to scientific inquiry. Many of its proposed levels seem to lie beyond the limits of observational verification, raising questions about whether such theories can ever be proven or falsified. Yet despite these challenges, several compelling lines of reasoning have been offered in support of the multiverse concept. These include indirect observational clues, theoretical consistency, and philosophical arguments rooted in logic, probability, and inference. 1. Observational clues, echoes at the edge of the cosmos. Some of the most tantalizing, albeit speculative, hints of the multiverse come from observations of the cosmos itself. While no telescope has peered into another universe, certain anomalies in cosmic data have prompted theorists to consider multiversal explanations. One example comes from irregularities in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. In 2010, data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite revealed peculiar cold spots and asymmetries in the CMB. While these could be statistical flukes or artifacts of local cosmic structures, some physicists speculated that they might be bruises caused by collisions with other universes. Bubble-like intrusions from neighboring realities in a Level 2 multiverse. Although this idea remains controversial and unconfirmed, it demonstrates that multiverse hypotheses can inspire observational predictions, however indirect or probabilistic they may be. 2. Inflationary theory predicts it. As discussed in Chapter 2, the theory of cosmic inflation is one of the strongest scientific arguments for the multiverse. Eternal inflation, in particular, seems to make the existence of a Level 2 multiverse virtually inevitable. Once inflation begins, it doesn't stop uniformly. Some regions slow down and form bubble universes, while others continue inflating. The result is a constantly expanding, ever-fragmenting space-time mosaic. What's significant is that inflationary models were originally developed to explain features of our own observable universe, such as its flatness, isotropy, and lack of magnetic monopoles, not to predict other universes. The multiverse is thus a natural consequence of a theory already supported by cosmic observations. As cosmologist André Linde, one of the pioneers of inflationary theory, put it, if you believe in inflation, you should also believe in the multiverse. 3. Quantum mechanics leaves little choice. The many-worlds interpretation, MWI, of quantum mechanics doesn't require extra postulates or exotic mechanisms. It emerges naturally from unitary evolution, the idea that the wave function evolves predictably according to the Schrödinger equation, without collapse. Unlike the Copenhagen interpretation, which relies on an observer-induced collapse, MWI treats all outcomes as real, occurring in separate branches. This avoids the need for a mysterious, non-physical process and provides a clear, deterministic account of quantum phenomena. In this framework, the multiverse isn't an added hypothesis, it's simply a recognition that all quantum possibilities are equally real. While MWI is not universally accepted, it has gained ground among physicists who favor a clean, unambiguous mathematical formalism. 4. The string landscape and fine-tuning. String theory, though not yet experimentally verified, offers a framework in which a vast number of possible physical realities can exist. The string landscape is a consequence of the way extra dimensions in string theory can be compactified. Each configuration leads to a different set of particle masses, coupling constants, and forces. With potentially 10 to the power of 500 viable configurations, the multiverse becomes a statistical necessity. This abundance of universes provides a natural solution to the fine-tuning problem, the observation that many physical constants appear just right for life to exist. In a single universe scenario, this fine-tuning seems improbable, possibly even miraculous. But in a multiverse of vast variety, it's not surprising that at least one universe has the conditions necessary for observers to exist. Here, the anthropic principle comes into play. If countless universes exist, only those that support observers like us will be observed, just as someone who wins the lottery doesn't question their luck, even if the odds were steep. 5. Philosophical and logical reasoning. Beyond empirical science, the multiverse is supported by philosophical arguments grounded in logic, probability, and epistemology. One such argument is based on Bayesian inference. If a multiverse can explain certain features of the universe more elegantly or completely than a single universe model, it may be rational to favor it, especially if it's a consequence of well-supported theories like inflation or quantum mechanics. Another comes from modal realism, the philosophical idea that all possible worlds are equally real. While this is often debated in metaphysics, it echoes the mathematical and level 4 multiverse proposed by Tegmark. If a mathematical structure can exist logically, then it exists physically. Furthermore, many physicists argue that mathematical elegance and explanatory power should be valued alongside testability, especially at the frontiers of theoretical physics. The multiverse may not be directly observable, but it provides a coherent and unifying framework that helps resolve numerous puzzles in cosmology, quantum mechanics, and particle physics. 6. The argument from absence of alternatives. Another subtle but powerful line of reasoning is that no better alternative exists. Take the inflationary multiverse. If eternal inflation follows naturally from the physics of scalar fields, as described in the inflationary model, and there is no known mechanism to stop it globally, then we must accept its consequences, including the multiverse it implies. Similarly, if quantum mechanics is correct and we reject arbitrary wave-function collapse, then MWI is hard to escape. While this absence of alternatives argument may not satisfy empirical purists, it reflects a pragmatic approach taken by many working physicists: accept the implications of your best theories, even if they challenge common sense. Chapter 5. Criticisms, counterarguments, and scientific skepticism. Despite its elegance and theoretical depth, the multiverse remains one of the most contentious ideas in modern physics. For many scientists and philosophers, it walks a fine line between bold theoretical insight and metaphysical speculation. While its proponents argue that it offers necessary explanations for otherwise baffling cosmic features, critics raise concerns about testability, falsifiability, and philosophical overreach. In this chapter, we will explore the primary criticisms of the multiverse, the responses from its defenders, and the broader implications these debates have for the philosophy of science. 1. The testability problem: is it even science? Perhaps the most persistent and central criticism of the multiverse hypothesis is that it is fundamentally untestable. By definition, if other universes exist beyond our causal horizon, or exist in separate quantum branches or mathematical realms, they cannot be observed, interacted with, or influenced. This appears to violate the principle of falsifiability, a core tenet of the scientific method as articulated by philosopher Karl Popper. According to Popper, a hypothesis must be disprovable in principle to be scientific. If no experiment could ever detect or refute the existence of other universes, then critics argue that the multiverse belongs in the realm of metaphysics or speculative philosophy, not empirical science. This challenge is especially acute for Level 2 and Level 4 multiverses. While Level 1 is an extrapolation of observable cosmology and Level 3 emerges from a valid interpretation of quantum mechanics, the deeper levels are accused of being epistemically unreachable. 2. Too many assumptions, the Occam's razor objection. Another major criticism invokes Occam's razor, the principle that, all else being equal, the simplest explanation is usually the best. Critics argue that invoking a near-infinite ensemble of universes to explain our own is an extravagant violation of simplicity. In this view, positing the existence of countless unseen realms, each with different laws and configurations, is a dramatic increase in theoretical baggage. Why multiply entities unnecessarily when more economical explanations, such as undiscovered laws within our own universe, might suffice? Multiverse defenders respond that simplicity isn't just about counting entities, it's about the simplicity of the laws, not the solutions. A theory that explains more with fewer assumptions, even if it implies many consequences, may still honor Occam's razor. 3. The anthropic principle, a philosophical cop-out? The anthropic principle, often cited to support the multiverse, has drawn sharp criticism. Detractors claim it functions as a philosophical escape hatch, used to dodge the responsibility of explaining fine-tuning by appealing to observer selection bias. Instead of seeking deeper physical causes for the precise values of constants, such as the cosmological constant or the strength of the strong nuclear force, anthropic reasoning shrugs, we observe these values because otherwise, we wouldn't be here to observe them. This logic, while tautologically true, is seen by critics as intellectually unsatisfying. It threatens to erode the explanatory power of science by replacing mechanism with mere selection. However, defenders counter that the anthropic principle is not an explanation in itself, but a filter, a statistical lens through which we understand probability distributions across many universes. If multiple realities exist, then the fact that we find ourselves in one that supports life becomes statistically inevitable, not philosophically empty. 4. Mathematical universe hypothesis, elegant or empty? Max Tegmark's Level 4 multiverse, that all mathematical structures are real, faces unique philosophical challenges. Critics argue that this is not science, but mathematical Platonism run wild. By equating mathematical existence with physical existence, Tegmark's view dissolves the distinction between the real and the imaginary. It leads to a bizarre ontology in which any logically coherent structure, no matter how alien or paradoxical, has a form of reality. Skeptics ask, what does it mean for a universe to exist if it has no physical instantiation or empirical consequences? Is mathematical existence sufficient? Can purely abstract objects bear the burden of physical causality? Tegmark responds by flipping the question, why do we assume that our physical reality is not mathematical at its core? If math explains everything we observe with astonishing precision, perhaps it's more than just a language, it's the fabric of reality itself. Still, the Level 4 hypothesis remains among the most speculative, and many physicists are hesitant to follow Tegmark to this abstract extreme. 5. The measure problem: how do you count infinities? Even if we accept the existence of multiple universes, a major problem arises: how do we calculate probabilities in an infinite multiverse? This issue, called the measure problem, plagues cosmologists trying to make predictions. In a multiverse where everything that can happen does happen, how do we distinguish between probable and improbable outcomes? How do we compare frequencies of events across infinite domains? Without a well-defined measure, the multiverse becomes predictively impotent. You can't meaningfully say what is likely or unlikely, because every outcome occurs an infinite number of times. Various proposals have been offered, such as the scale factor cutoff and comoving volume weighting, but no consensus has emerged. Until this foundational issue is resolved, the multiverse remains probabilistically unstable. 6. Identity and consciousness in a multiverse. A lesser-known but fascinating critique centers on personal identity. If every version of you that could exist does exist somewhere, each branching at every quantum decision, what does this say about the nature of the self? Are these other yous truly you? If a copy exists in another universe who made different choices, how do we define individual identity across the multiverse? This is not merely a philosophical puzzle, it also has implications for ethics, responsibility, and even free will. Multiverse proponents often embrace a view of consciousness as a process bound to a single world line, a thread through the multiverse. But this is an area where science meets metaphysics, and no clear answers yet exist. 7. Scientific conservatism: why not wait? Finally, many critics adopt a conservative stance: let's wait. They argue that science advances best by slow, steady, empirical progress, not by speculative leaps. The multiverse, in their view, may someday be supported by new physics or observational techniques, but for now, it risks distracting from falsifiable, grounded theories. They urge a focus on theories that produce concrete, testable predictions about our own universe, rather than abstract conjectures about countless invisible ones. This caution echoes a long tradition in science, from Newton's rejection of action at a distance to Einstein's discomfort with quantum randomness. In time, what seems speculative may become standard, but only with evidence. Chapter 6: The Multiverse in Popular Culture and Human Imagination. Beyond laboratories and theoretical papers, the multiverse has flourished in the collective imagination. The idea that reality may consist of many parallel or alternate worlds has captivated storytellers, philosophers, mystics, and artists for centuries. Long before it became a serious scientific hypothesis, the multiverse existed in myths of other realms, spiritual cosmologies, and science fiction's what-if scenarios. Today, it remains a favorite theme in films, novels, games, and speculative fiction, not merely for its narrative power, but because it resonates with deep psychological and existential questions. This chapter traces the cultural evolution of the multiverse, examining how it has served as a mirror for human desires, fears, and identity. 1. Ancient echoes: many worlds before modern science. The notion of multiple worlds is not exclusive to modern physics. Ancient Hindu cosmology, for example, spoke of a cyclic universe, with endless births and destructions, each a realm governed by different laws and deities. The Vedic texts refer to numerous lokas, or planes of existence, which differ in quality, time perception, and energy. Similarly, Buddhist cosmology describes a multiverse of countless world systems, each with its own heavens, hells, and mortal realms. In ancient Greece, philosophers like Anaximander and later Democritus speculated about infinite worlds scattered through boundless space, some possibly devoid of life, others perhaps similar to Earth. Even Epicurus proposed a universe teeming with countless worlds formed by the random motions of atoms. These early visions were not scientific in the modern sense, but they reflect a persistent intuition that reality may be more expansive and layered than we perceive. 2. The multiverse as a narrative device in fiction. In modern literature and media, the multiverse provides an endlessly flexible storytelling engine. It allows authors to explore counterfactual histories, alternate selves, moral dilemmas, and speculative technologies without violating narrative continuity. It creates spaces for imagination to roam, unrestricted by the limitations of a single timeline or causal chain. In literature, Jorge Luis Borges's 1941 story The Garden of Forking Paths may be one of the earliest literary explorations of a multiverse. Portraying time as a branching structure where all possible futures exist simultaneously. Later, Philip K. Dick and Ursula K. Le Guin embraced similar themes, weaving alternate realities into their philosophical science fiction. In comic books, multiverses became central to publishers like DC and Marvel. DC Comics' Crisis on Infinite Earths and Marvel's Secret Wars employed the multiverse to reset, merge, or reimagine characters and timelines. These stories reflect not only narrative convenience, but deeper questions about identity, consequence, and fate. In cinema, the multiverse has surged into mainstream consciousness. Films like The Matrix, 1999, Inception, 2010, Interstellar, 2014, and Everything Everywhere All at Once, 2022, dramatize the idea that reality is not singular or stable. Marvel's recent Multiverse saga explicitly foregrounds alternate universes, bringing this once esoteric concept into global popular culture. Such narratives often blend science with metaphor, allowing audiences to ponder questions like, what if I had chosen differently? Is there another me out there? Could destiny be rewritten? 3. Multiverses and the psychology of possibility. Why is the multiverse so compelling to the human psyche? At its core, it taps into a profound psychological tension, the desire for freedom and the weight of consequence. The idea that every choice spawns a new universe can be liberating. It implies that no possibility is ever truly lost, that all versions of ourselves exist somewhere, living out every dream and regret. This provides a strange kind of existential comfort. Even in a life filled with missed chances or painful outcomes, the multiverse whispers, another you made it. This idea also intersects with trauma and healing. Some psychotherapists and philosophers have explored the multiverse metaphor as a way to process regret or guilt. Encouraging clients to imagine a self who chose differently, and to integrate that imagined self into healing narratives. But this psychological richness comes with disquieting questions. If all realities happen, does choice lose meaning? If every possible you exists, what makes you special? In this way, the multiverse becomes not just a scientific or narrative idea, but a mirror of personal identity, refracting it into infinite variations. 4. Spiritual and mystical multiverses. The multiverse has also resonated with spiritual and mystical traditions, often under different names. In Kabbalistic Judaism, the concept of the four worlds represents layers of reality, each more abstract and divine than the last. In Sufism, the notion of multiple planes of reality, from the material to the spiritual, mirrors multiversal thinking. In Western esotericism, thinkers like Emanuel Swedenborg describe traveling through various heavens and hells, each with its own rules, beings, and moral logic. The Theosophical tradition, influential in the late 19th and early 20th centuries, spoke of astral and causal planes, realms of existence beyond physical perception. Even in contemporary New Age spirituality, the multiverse has found a home. Ideas of parallel lives, quantum jumping, and vibrational worlds draw, however, loosely from the language of quantum theory to support metaphysical beliefs about manifestation, soul journeys, and higher dimensions. While these interpretations lack scientific rigor, they demonstrate the multiverse's deep symbolic power, as a way to imagine transcendence, transformation, and the mystery of being. 5. Art, games, and the aesthetics of multiplicity. In the visual arts, the multiverse has inspired styles that emphasize fracture, simultaneity, and layered realities. From cubism's fragmented perspectives to digital media's overlapping interfaces, artists have long explored the aesthetics of multiplicity. In gaming, the multiverse is not merely a theme but a structure. Role-playing games, simulation games, and alternate-ending narratives all rely on the idea that choices can lead to different worlds. Games like BioShock Infinite, The Legend of Zelda, Ocarina of Time, and the Stanley Parable explicitly play with multiversal mechanics, encouraging players to explore what could have been. This interactivity makes the multiverse not just a story, but a playable philosophy. Players experiment with causality, consequence, and moral ambiguity, mirroring the scientific and existential questions at the heart of multiverse theory. 6. The multiverse as modern myth. Ultimately, the multiverse has become a kind of modern myth. A shared conceptual framework that allows people to grapple with complexity, chance, and identity in a rapidly changing world. As mythologist Joseph Campbell observed, every era invents myths that reflect its technological and psychological landscape. For an age of quantum computing, artificial intelligence, and deep space telescopes, the multiverse is an apt symbol. It speaks to uncertainty and potential. It evokes wonder and humility. And like all enduring myths, it leaves room for both science and mystery. Chapter 7: The Future of Multiverse Research and What It Means for Us All. As the multiverse theory continues to develop, it is no longer a fringe curiosity, it is increasingly a frontier. Its implications stretch beyond physics and cosmology into philosophy, technology, and even questions of meaning and human destiny. What was once dismissed as speculative is now a serious, albeit controversial, subject of academic inquiry. This final chapter explores where multiverse research might go next, how it could evolve with new discoveries, and what it ultimately means for science, society, and our place in reality. 1. Experimental frontiers. Can we ever prove the multiverse? Perhaps the most pressing question facing multiverse theorists is this: can we ever test it? Despite current skepticism, researchers are investigating several strategies for gathering indirect evidence. Cosmic signatures, such as anomalies in the cosmic microwave background, CMB, could suggest collisions with other bubble universes in a Level 2 multiverse. A cold spot in the CMB, for instance, has been interpreted by some as a possible bruise from such an encounter, though this remains highly debated. Gravitational waves offer another frontier. As detectors become more sensitive, we may be able to observe ancient ripple patterns that reflect early universe processes, potentially including inflationary scenarios that imply a multiverse. In the quantum domain, researchers are exploring quantum decoherence, quantum computing, and entanglement as avenues to probe the nature of branching universes, Level 3. If different quantum branches can leave detectable interference patterns, it might one day support many worlds theory. While these tests are difficult, they're not impossible, and as technology advances, what now seems metaphysical may become empirical. 2. Bridging theories, from quantum gravity to information theory. Another direction for multiverse research lies in unifying existing theories. String theory, loop quantum gravity, and causal set theory are all candidates for a theory of everything, and each has implications for how a multiverse might be structured or emerge. String theory, in particular, naturally leads to the concept of a landscape of vacuum states, each corresponding to a different universe with its own laws. These models attempt to reconcile general relativity and quantum mechanics and are being refined through mathematical rigor and theoretical innovation. Meanwhile, researchers are increasingly seeing information as fundamental. From black hole entropy to quantum entanglement, information theory is shaping how we think about spacetime, matter, and even existence itself. Some theorists suggest that the multiverse is ultimately a vast information structure, and we are patterns within it. This convergence of disciplines may offer new ways to formalize and test multiverse models, especially as AI and machine learning tools begin to help analyze and simulate complex physical systems. 3. Philosophical evolution. Redefining reality. The multiverse has already begun to reshape philosophical discussions. In metaphysics, it reopens old debates about determinism, identity, and modal realism, the idea that all possible worlds are as real as the actual one. The multiverse lends weight to philosophers like David Lewis, who long argued for the equal reality of all possible worlds. In ethics, it raises new questions. If all outcomes occur somewhere, does that reduce moral responsibility in any one branch? Does it make sense to talk about moral progress if every possible action is taken by some version of humanity? In epistemology, the study of knowledge, the multiverse forces us to re-examine what we mean by knowing something. If we're in one of countless realities, and our observations are shaped by selection effects, how can we claim objective knowledge of reality as a whole? These questions aren't just theoretical. They touch how we think, how we live, and how we teach future generations about their place in the cosmos. 4. Cultural transformation, a new cosmic perspective. The Copernican revolution displaced Earth from the center of the universe. The multiverse may displace our universe itself from the center of existence. This shift could provoke a profound cultural transformation. Just as the idea of evolution altered how we view human origins, and relativity reshaped our understanding of time, the multiverse challenges the very uniqueness of our cosmos. It implies that our universe is not special by virtue of its existence alone, only by virtue of its capacity to host observers like us. This is a deeply humbling view. It replaces the cosmic spotlight with a cosmic spectrum. But it can also be empowering. If reality is infinite in scope and depth, then our pursuit of knowledge, creativity, and ethics becomes part of a larger, more mysterious story. 5. Technological implications, computing the cosmos. The multiverse may also have implications for technology, especially quantum computing and simulation theory. Some interpretations suggest that quantum computers may exploit branching realities to perform certain calculations, using many worlds as a kind of computational substrate. Moreover, the multiverse intersects with the idea that our universe might itself be a simulation. If all mathematically possible realities exist, as Tegmark's level 4 implies, then simulated universes may vastly outnumber base ones. This leads to the provocative simulation argument. It might be more probable that we live in a simulated multiverse than a physical one. Though speculative, these ideas are shaping research in complex systems, machine learning, and digital physics, and could redefine what we think of as real. 6. A new humanism, living in a multiverse. Finally, what does it mean, existentially, to live in a multiverse? Does it make life meaningless, or more meaningful? On one hand, the idea that every possibility occurs somewhere might seem to rob our choices of significance. If every outcome happens, then why strive? But this interpretation misses a crucial point: you still experience only one branch. Your decisions still matter, for you, and for those around you. The multiverse doesn't negate meaning, it deepens it, by showing that each moment of choice is a node of branching significance. Moreover, it evokes awe. It situates us in a cosmos of infinite stories, countless beings, and endless mysteries. It reminds us that we are part of something far greater than ourselves, and that curiosity, compassion, and creativity are the lights we carry into the vast unknown. Conclusion: one universe among many. The multiverse theory is not yet proven, nor universally accepted. It may take decades, or centuries, for it to be confirmed, refuted, or transformed beyond recognition. But it represents a bold step in the grand human endeavor to understand reality. Whether as a scientific model, a philosophical idea, or a cultural myth, it challenges us to think bigger, deeper, and wider than ever before. In contemplating the multiverse, we are not merely gazing at distant stars or imagined dimensions. We are asking the oldest and deepest questions: who are we? Why is there something rather than nothing? What else might exist beyond the veil of perception? The answers may lie not just in one universe, but in many. A glimpse into the unthinkable. When pondering the depths of space, few concepts are as profoundly mysterious as black holes, those insatiable cosmic entities from which nothing, not even light, can escape. But what if there existed a mirror image of these gravitational monstrosities? An object that doesn't devour but expels, a region of spacetime where matter bursts forth rather than gets crushed inward? This is the idea behind white holes. A theoretical solution to Einstein's field equations that has both fascinated and puzzled physicists for decades. A white hole is essentially the time-reverse twin of a black hole. While black holes are defined by their event horizons that trap all incoming matter and radiation, white holes are characterized by event horizons that allow only outward flow. Nothing can enter a white hole from the outside, just as nothing can escape a black hole from within. It is as if the universe has engineered a perfect one-way exit, the ultimate cosmic repulsion. Though purely theoretical at this point, white holes are not just science fiction or whimsical musings. They emerge naturally from the same mathematical framework that predicted black holes long before any were observed. In fact, some scientists argue that if we are to take general relativity seriously, then we must grapple with the possibility of white holes. More than a curious mirror, white holes could have implications for our understanding of entropy, the arrow of time, cosmic censorship, and even the origin of our universe. In this comprehensive exploration, we will dive deep into the theory of white holes, tracing its origins, its place within general relativity, the mathematics that governs it, and the current debate surrounding its viability. We'll consider its relationship to black holes, the controversial hypothesis of white holes as black hole endpoints or wormhole exits, and examine the potential observational signatures that could one day validate their existence. In doing so, we will peel back the layers of one of modern physics' most intriguing puzzles: the origins of the white hole concept. To understand white holes, we must first appreciate the mathematical and conceptual framework from which they arise. Albert Einstein's theory of general relativity. Developed in 1915, this revolutionary theory redefined gravity not as a force but as the curvature of spacetime caused by mass and energy. Einstein's equations describe how matter and energy determine the geometry of spacetime and how that geometry, in turn, affects the motion of matter and energy. From these equations came a host of fascinating solutions. Among them, the Schwarzschild solution, which describes the spacetime geometry around a non-rotating, spherically symmetric mass. First derived by Carl Schwarzschild in 1916, this solution laid the foundation for what we now call black holes. It predicted the existence of a critical radius, later dubbed the event horizon, beyond which escape becomes impossible. However, the Schwarzschild solution has more to offer. It also implies, under idealized conditions, a region of spacetime that is essentially the time reversal of a black hole, a white hole. In fact, when one fully extends the mathematical solution for a Schwarzschild black hole using a so-called maximally extended Kruskal-Zuccari's diagram, both a black hole and a white hole appear as part of the same spacetime structure. These diagrams show not only our own universe and a black hole, but a white hole and an entirely separate, causally disconnected universe, what some refer to as a parallel universe. This was not just a quirk of mathematics. It revealed a deep symmetry in the equations of general relativity, a symmetry between the past and the future, between infall and ejection, between black holes and white holes. The physical interpretation of this mathematical elegance, however, remains one of the most contentious issues in theoretical physics. Understanding the Kruskal extension. To further grasp what a white hole entails, we need to delve into the concept of the Kruskal-Zacharias extension. The Schwarzschild metric in its basic form becomes singular at the Schwarzschild radius, suggesting a breakdown of spacetime. But this is merely a coordinate singularity, something that can be resolved by changing the coordinate system. When this is done through the Kruskal-Zacharias transformation, the new coordinate system reveals a much richer structure. In Kruskal-Zacharias coordinates, the Schwarzschild geometry does not merely describe the exterior of a black hole and its interior leading to a singularity. Instead, it includes four distinct regions. 1. Region I, the universe outside the black hole, our observable universe. 2. Region II, the interior of the black hole, what lies within the event horizon. 3. Region III, a white hole region, connected to region I but characterized by a horizon from which matter can emerge but not enter. 4. Region IV, a second universe, causally disconnected from region I, possibly linked through the black and white holes. This extended manifold shows that black holes and white holes are not merely separate objects but can be part of a single, interconnected spacetime fabric. At least in theory. These extensions offer a mathematical playground where the full implications of Einstein's equations can be studied without the constraints of physical realism. But are they just mathematical abstractions, or do they hint at a deeper truth about the nature of the cosmos? Black holes and time reversal symmetry. One of the most profound aspects of general relativity is its inherent time reversal symmetry. The equations of motion that govern the curvature of spacetime are indifferent to the direction of time. This means that if a particular process is allowed by the laws of physics, then its time-reversed counterpart must also be allowed. A black hole, which forms from the gravitational collapse of a massive star, has as its time reverse a white hole, an object that expels matter and energy into the universe rather than pulling it in. This symmetry is both beautiful and troubling. In the real universe, we observe black holes forming from stellar collapse and merging in violent cosmic events. But we have never observed a white hole, nor do we see evidence of anything that behaves in such a manner. This asymmetry suggests that while the equations of general relativity may allow white holes, the boundary conditions of our universe do not. One possible reason for this lies in the nature of entropy and the arrow of time. Black holes represent a state of maximal entropy, the ultimate sink of disorder. A white hole, by contrast, would be a highly ordered, low-entropy configuration that would have to emit matter in a precisely tuned manner. Such precision seems wildly improbable in a universe that tends toward increasing disorder. Thus, the arrow of time may play a role in favoring black holes over white holes, even if both are mathematically permitted. The singularity at the core. Both black holes and white holes contain a central singularity. A point where the curvature of spacetime becomes infinite, and the known laws of physics cease to function. In the case of black holes, matter and energy are crushed to infinite density at the singularity, which is hidden from the rest of the universe by the event horizon. This cosmic censorship ensures that singularities remain hidden, preserving the predictive power of general relativity. White holes also possess a singularity, but of a different kind. Instead of pulling matter in, the white hole's singularity spews it out. It serves as the past boundary of spacetime rather than the future endpoint. The idea of matter suddenly emerging from a singularity, already in motion, with no apparent cause or prior state, presents a serious challenge to causality and determinism. It implies that some regions of spacetime may emerge spontaneously, without a past, simply as a boundary condition. These strange features have led many physicists to doubt whether white holes can be considered physically plausible objects. Still, others argue that these peculiar properties may hold the key to understanding deep questions about the universe's origins and the ultimate fate of matter inside black holes. Modern interpretations and challenges. While the classical white hole is a compelling mathematical curiosity, it faces numerous obstacles when considered from the standpoint of physical realism. Chief among these is stability. A white hole, by definition, cannot allow matter or energy to enter. But the moment any material object approaches the white hole's event horizon, its mere presence seems to destabilize the configuration. Calculations suggest that the tiniest perturbation would cause the white hole to collapse into a black hole, thereby eliminating its unique time-reversed characteristics. Furthermore, white holes seem to violate the second law of thermodynamics. They imply a spontaneous decrease in entropy, a reversal of the natural order. In a universe governed by entropy increase, where disorder always grows, the sudden, coherent ejection of matter from a white hole seems paradoxical. It's as if a broken egg unscrambles itself and leaps back onto the table. Nevertheless, the notion of white holes has undergone a renaissance in recent years, driven by advances in quantum gravity, the information paradox surrounding black holes, and new ideas in loop quantum gravity and holography. Some researchers now entertain the possibility that white holes might not only be real but essential to understanding the ultimate fate of black holes and the unification of general relativity with quantum mechanics. From classical to quantum, new hope for white holes. Classical general relativity, despite its elegance, begins to crumble at singularities, those infinitely dense regions predicted at the centers of black holes and white holes. The infinite curvature and breakdown of spacetime imply that general relativity is incomplete, it cannot describe what happens at the heart of these extreme environments. This is where quantum gravity steps in, the effort to unify Einstein's general relativity with quantum mechanics. In recent decades, a number of approaches to quantum gravity have gained traction. Among them, loop quantum gravity, LQG, and string theory stand out. Of these, LQG has provided perhaps the most promising framework in which white holes can be reimagined as physically viable rather than purely theoretical entities. Rather than treating white holes as eternal and idealized objects, as in the Kruskal extension, quantum gravity introduces a dynamic evolution of spacetime itself. In particular, it opens the door to the fascinating idea that black holes might not mark the end of spacetime but rather a transitional phase, a bounce that culminates in a white hole. This quantum reinterpretation transforms the white hole from a bizarre, unstable abstraction into a crucial part of the black hole life cycle. The bounce hypothesis, black hole to white hole transition. The black hole bounce hypothesis has emerged as one of the most intriguing developments in theoretical physics. This idea suggests that when matter collapses into a black hole, it does not vanish into a singularity but instead undergoes a quantum gravitational transformation. Eventually, it rebounds and emerges as a white hole. This is reminiscent of loop quantum cosmology, a branch of LQG that resolves the Big Bang singularity by replacing it with a big bounce. Just as the universe might have rebounded from a previous collapsing phase, perhaps matter falling into a black hole rebounds into a white hole, ejecting information and energy back into spacetime. Carlo Rovelli and Francesca Vidato, among the leading proponents of this idea, propose that the black hole interior undergoes quantum evolution into a white hole. This transformation doesn't require an external observer or external time, it happens in a timeless, quantum way. According to their calculations, the bounce could take place very rapidly from the point of view of the internal observer, but appear to take an astronomically long time from the perspective of an outside observer due to extreme gravitational time dilation. This delay could help explain why we haven't yet seen any white holes. They may still be forming inside black holes, with the outward burst of energy yet to occur. Planck stars, the intermediate phase. In this framework, a new concept emerges, the Planck star. Named after the Planck scale, the realm where quantum gravity effects dominate, Planck stars are hypothesized to be the quantum-resolved cores of black holes. They are ultra-compact objects that resist collapse due to quantum gravitational pressure, much like how neutron stars resist gravity through neutron degeneracy pressure. The idea is that as matter compresses within a black hole, quantum effects become increasingly dominant and eventually halt the collapse. This core region becomes a Planck star, storing the information and mass until it can be released via the white hole transition. When the transition completes, a white hole forms at the location of the former black hole, expelling the information in a process that avoids information loss. Planck stars are an elegant solution to several problems in black hole physics, including the black hole information paradox, the conundrum of whether information that falls into a black hole is truly lost forever. In the white hole bounce scenario, the information is not destroyed but rather stored temporarily and then returned to the universe through the white hole phase. The timescale dilemma, external versus internal clocks. A critical question in this model concerns the timescales involved. How long does the black hole-white hole transition take? Inside the black hole, the transformation to a white hole could occur in mere milliseconds or seconds, depending on the internal observer's frame of reference. However, for an external observer, the time dilation near the event horizon becomes so extreme that the bounce might take billions, or even trillions, of years. This phenomenon arises from the nature of relativistic time. The deeper one is in a gravitational well, the slower time moves relative to a distant observer. As such, a Planck star might already be in the process of becoming a white hole, but from our vantage point, we simply haven't seen it happen yet. In practical terms, white holes may be the extremely long-term fates of all black holes in the universe. This resolution is philosophically satisfying. It preserves unitarity, the principle that quantum information is never lost, solves the singularity issue, and respects both quantum mechanics and general relativity in their respective domains. Thermodynamics and entropy revisited. One of the long-standing objections to white holes has been their apparent violation of the second law of thermodynamics. White holes seem to represent highly ordered states from which matter and radiation emerge spontaneously. Something that would entail a massive local decrease in entropy. But in the quantum gravity model, entropy is not violated, it is transformed and delayed. During the black hole phase, entropy increases as expected. The information is compressed but not destroyed, it is encoded on the black hole's event horizon as per the holographic principle. The quantum bounce then redistributes this information through the white hole phase, preserving the overall entropy balance. In this framework, white holes are not low-entropy sources, but restructured, high-entropy outcomes of gravitational collapse. The radiation and information they release are scrambled, not pristine. In fact, the emitted radiation might resemble Hawking radiation, preserving the black hole's thermodynamic consistency. Quantum foam and wormholes. Another avenue where white holes enter the quantum realm is through the concept of quantum foam. At the smallest scales, on the order of the Planck length, spacetime is thought to be turbulent and discontinuous, fluctuating wildly due to quantum uncertainty. Within this foam, micro-wormholes might constantly open and close, potentially linking distant parts of spacetime. Some speculative models propose that white holes could exist as the exit mouths of traversable wormholes, with black holes serving as the entrances. This idea links white holes not only to the future of black holes but also to faster-than-light travel and even time travel. However, the stability of such wormholes is dubious. Traversable wormholes would require exotic matter with negative energy density to remain open, substances that, while not impossible in theory, have never been observed. Nevertheless, these ideas illustrate how white holes inhabit a central role in speculative physics, where the boundaries of the known are pushed to their limits. The holographic principle and information recovery. One of the most important developments in theoretical physics over the past few decades is the holographic principle. Proposed by Gerard T. Hooft and expanded by Leonard Susskind, this principle suggests that all the information contained within a volume of space can be encoded on its boundary surface. This insight gained powerful traction in black hole physics when it was applied to the event horizon of black holes. According to this principle, the seemingly lost information inside a black hole is not destroyed but encoded on the surface in a highly scrambled form. In quantum gravity models where black holes evolve into white holes, the holographic principle plays a critical role. It ensures that all information can, in principle, be recovered and re-emitted. This re-emission would occur through the white hole phase, potentially solving the information paradox and preserving the fundamental tenets of quantum mechanics. In such a model, black holes are temporary prisons of information, and white holes are the long-awaited keys to release it back into the universe. Echoes from the edge, searching for white hole signatures. A theoretical model gains credibility when it makes testable predictions. In the case of white holes, especially those emerging from quantum gravity theories, several potential observational consequences arise: primordial white hole explosions. Some theorists suggest that white holes could have formed in the early universe and are only now reaching the end of their bounce phase, emitting bursts of radiation. These explosions might resemble fast radio bursts, FRBs, or gamma-ray bursts, enigmatic phenomena still not fully understood. Echoes and gravitational waves. When black holes merge, they produce gravitational waves detected by observatories like LIGO and Virgo. Some theories predict that if a white hole forms from the remnant, it may produce a secondary echo signal after the main merger event. These echoes could serve as fingerprints of quantum gravitational bounce. Cosmic ray anomalies. Ultra-high-energy cosmic rays that appear to have no clear source might be remnants of distant white hole emissions. If white holes can emit particles with extreme energies, they could help explain these cosmic mysteries. While none of these observations provide conclusive evidence, the mere possibility of falsifiable predictions distinguishes the quantum white hole theory from more abstract speculations. The white hole Big Bang hypothesis. Among the most provocative ideas in modern theoretical physics is the suggestion that the Big Bang itself may have been a white hole. This hypothesis, while speculative, finds resonance in various lines of thought that attempt to connect cosmology with black hole physics. The key idea is that the universe's birth was not an emergence from nothing, but rather the outcome of a quantum gravitational process akin to the black hole to white hole bounce. Let's consider a scenario. A collapsing star forms a black hole. Inside that black hole, spacetime continues to curve, reaching what appears to be a singularity. However, instead of terminating reality, quantum gravity forces kick in, causing a rebound. The energy and information within the black hole are ejected through a white hole, possibly into another region of spacetime or even into a separate universe. If such a white hole serves as the seed of a new universe, then every black hole might, in principle, be a cosmic womb, a cradle for a new reality. Applied to our own universe, this suggests that the Big Bang was the white hole end of such a process. Our cosmos could have been born from the interior of a black hole in a parent universe, connected through a now severed wormhole or Einstein-Rosen bridge. This would mean our universe is causally disconnected from its parent but still physically descended from it. This view elegantly sidesteps the troubling notion of a true singularity at the beginning of time. Instead of a point of infinite density and temperature, the Big Bang becomes a quantum bounce, preserving continuity and perhaps even causality from an earlier phase of existence. The arrow of time and entropic reversal. If white holes are time-reversed black holes, then what do they tell us about the arrow of time? In thermodynamics, the arrow of time points in the direction of increasing entropy. In classical physics, time is symmetric. The laws don't care whether you run events forward or backward. But in our universe, time very clearly moves in one direction, forward, from past to future. White holes, as time-reversed black holes, seem to defy this arrow. While black holes absorb matter and increase entropy, white holes expel matter in an apparently entropy-reducing act. This has long been one of the biggest theoretical objections to white holes. However, when viewed through the lens of quantum cosmology, the picture becomes more nuanced. If the universe began as a white hole, then the outward flow of matter and radiation might be the origin of our time arrow. The low-entropy state of the early universe, another great mystery, could be explained by the white hole's emission phase. The white hole would not violate thermodynamics; instead, it would serve as the entropy ground zero from which complexity unfolds. Furthermore, if every black hole evolves into a white hole over vast time spans, then time might reverse within those systems, creating causally disconnected regions where time flows differently. This opens doors to ideas like temporal duality, mirror universes, or even antiverses. Mirror reflections of our universe evolving backward in time relative to us. White holes and the cyclic universe. The idea of a cyclic universe, one that goes through infinite cycles of expansion and contraction, has ancient roots and modern revival. In these models, each Big Crunch, a contracting phase, is followed by a new Big Bang, an expanding phase. But what mechanism triggers this rebirth? White holes may provide the answer. In certain formulations of loop quantum gravity and ekpyrotic cosmology, the universe doesn't end in a singular collapse. Instead, when spacetime contracts to a critical density, it undergoes a quantum bounce and rebounds outward again. This rebound could take the form of a white hole, releasing the contents of the old universe into a new phase of expansion. In this view, each universal cycle is a black hole to white hole transition on a cosmic scale. The death of one cosmos seeds the birth of the next. Time, energy, and structure are recycled, perhaps endlessly, through this white hole mechanism. Some versions of this theory suggest that the information of past universes might be retained, albeit in highly scrambled form. Thus, white holes could be not only birthplaces but memory vaults of cosmic history, their emissions holding traces of what came before. Multiverse implications, black holes as portals. The black hole-white hole framework also intersects with the multiverse theory, the idea that our universe is just one of many. If black holes can spawn white holes that birth new universes, then each black hole could be a gateway to a new cosmos. This notion redefines black holes not as dead ends but as cosmic seeds. Each universe may have its own physical laws, constants, and initial conditions, determined by quantum fluctuations at the bounce point. Some universes may be brief and chaotic. Others long-lived and stable, like ours. This ties closely to Lee Smolin's theory of cosmological natural selection, which proposes that universes evolve through black holes. Those with physical constants favorable to black hole formation reproduce more often, passing on their traits. Over time, a kind of Darwinian process shapes the multiverse. White holes, in this theory, are the birth canals of this cosmic evolutionary process. Though speculative, this vision gives purpose to black holes and white holes alike. They become engines of creation, not just destroyers or oddities. Consciousness, observation, and white holes. An even more speculative avenue of thought links white holes to consciousness and observation in quantum mechanics. Some thinkers have drawn analogies between white holes and the observer effect, the idea that observation collapses a quantum wave function into a definite state. Could white holes represent the projection of information into a new spacetime, similar to how observation projects a quantum system into classical reality? In this metaphor, black holes absorb potentialities, while white holes realize outcomes. Though this analogy stretches the boundaries of rigorous science, it highlights the deep entanglement between white holes, information, and the nature of reality. Further still, some fringe theories suggest that consciousness itself might be connected to the informational geometry of spacetime, perhaps even involving mini white hole-like structures in the brain. These ideas remain highly controversial and lack empirical support, but they demonstrate how white holes provoke philosophical inquiry as much as physical investigation. White holes and the simulation hypothesis. Another modern philosophical idea, the simulation hypothesis, suggests that reality as we know it may be a sophisticated simulation, perhaps run by an advanced civilization or future version of ourselves. In this digital universe metaphor, black holes and white holes might serve as computational functions or data portals. Some physicists and philosophers speculate that black holes could function as data compression nodes, where vast quantities of information are condensed. White holes, by contrast, would be data decompression events, where the information is re-expanded and reintegrated into a new system. This mirrors the holographic principle and quantum bounce ideas but recasts them in computational terms. If the universe is code, then perhaps white holes are subroutines that output evolved states, simulations seeded by compressed prior data. Again, while speculative, these ideas demonstrate the interdisciplinary reach of white holes. From hard physics to deep metaphysics. Rewriting the cosmic story. For over a century, black holes have fascinated and terrified us, cosmic monsters from which nothing escapes. But with the rise of quantum gravity and new cosmological models, a richer narrative unfolds, one in which black holes evolve, transform, and perhaps even create. In this tale, white holes are the long-forgotten second act, the phoenix reborn from the gravitational fire. Whether as endpoints of black holes, creators of universes, or metaphysical symbols of renewal, white holes challenge our assumptions. They turn death into rebirth, endings into beginnings, entropy into possibility. The white hole is more than a mirror, it is a portal to new understanding. It asks us to reconsider not only how the universe works, but how it began, how it might end, and what lies beyond the horizons of our current knowledge. Deep dive on dark matter and dark energy. Part 1: Foundations of Cosmology. In the vast expanse of the universe, what we can see, touch, and measure is only a small fraction of what actually exists. Stars, planets, and galaxies, everything made of atoms, constitute less than 5% of the total cosmos. The remaining 95% is composed of two of the most mysterious components ever theorized, dark matter and dark energy. These two concepts are among the most profound mysteries of modern physics and cosmology, representing the unseen forces and substances that govern the behavior of the universe at the largest scales. Dark matter and dark energy are not simply theoretical constructs, their existence is supported by extensive observational evidence, yet their nature remains elusive. In this deep dive article, we will explore the origins of the dark matter and dark energy theories, the scientific discoveries that led to their recognition, and the ongoing efforts to understand them. Our journey will take us through the early history of cosmology, the revolutionary discoveries of the 20th century, the current scientific consensus, and the frontiers of modern research. To understand dark matter and dark energy, we must begin with the history of cosmology. From ancient civilizations that saw the universe as a finite dome above a flat Earth, to the heliocentric model of Copernicus, and finally to the expansive and dynamic cosmos described by Einstein's theory of general relativity, our understanding of the universe has continuously evolved. Part 2: The discovery of dark matter. Dark matter is one of the greatest enigmas of the cosmos. Its existence was first suggested when astronomers noticed that galaxies were rotating at speeds that seemed impossible given their visible mass. If galaxies were made up solely of the stars, planets, and gas that we can observe, they would fly apart due to their rapid rotation. Yet they hold together, suggesting the presence of an unseen mass exerting a gravitational force. Fritz Zwicky and the missing mass problem. The story of dark matter begins in the 1930s with Swiss astronomer Fritz Zwicky, who studied the Coma galaxy cluster. Using the virial theorem, a principle of classical mechanics, Zwicky calculated the total mass of the cluster based on the motion of galaxies within it. To his astonishment, he found that the visible mass of the galaxies was far too low to account for the gravitational forces holding the cluster together. He called this hidden mass, Dunkel Materie, dark matter. Zwicky's discovery was groundbreaking, but it was largely ignored at the time. His calculations were considered too crude, and the idea of an invisible form of matter was too radical for most astronomers. Vera Rubin and galactic rotation curves. In the 1970s, American astronomer Vera Rubin and her collaborator Kent Ford used high-precision spectrographs to measure the rotation curves of spiral galaxies. What they found was shocking. Stars at the outer edges of galaxies were moving just as fast as those near the center. According to Newtonian mechanics, these stars should have been moving slower due to the weaker gravitational pull far from the galaxy's core. But they weren't. Rubin's work provided the strongest evidence yet that galaxies were enveloped in massive, invisible halos of dark matter. Her research was meticulous, and her data was undeniable. Dark matter was no longer just a theoretical idea. It was a fundamental aspect of our understanding of the universe. The nature of dark matter, hypotheses and theories. But what is dark matter? Scientists have proposed several possibilities, including WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and the weak nuclear force. They are the most popular dark matter candidate and are the focus of many large-scale experiments. Axions. Ultralight particles predicted by certain theories of particle physics, which could also account for dark matter. Sterile neutrinos, a hypothetical type of neutrino that does not interact via the weak nuclear force but could be a component of dark matter. Machos, massive compact halo objects. These are not exotic particles, but rather normal objects like black holes, neutron stars, or brown dwarfs that are simply hard to detect. Yet, despite decades of research, dark matter has never been directly detected. Advanced detectors, from underground laboratories to space-based observatories, have searched for signs of dark matter particles, but all have come up empty so far. The role of dark matter in cosmic structure formation. Dark matter is not just an invisible presence, it is a cosmic architect. In the early universe, dark matter formed vast, invisible webs, attracting normal matter through gravity. Over time, this normal matter collected in the densest regions of the dark matter web, leading to the formation of galaxies, stars, and planets. Without dark matter, the universe would look very different. Galaxies might never have formed, and the grand cosmic structures we see today would not exist. Dark matter is the silent, invisible skeleton of the universe. Part 3: The Discovery of Dark Energy. If dark matter was a revelation about the hidden mass of the universe, dark energy was an even more profound shock. Unlike dark matter, which exerts a gravitational pull, dark energy appears to do the opposite: it drives the universe apart. The story of dark energy begins in the late 20th century, with a discovery that defied all expectations. The accelerating universe. In the 1990s, two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were observing distant Type Ia supernovae. These supernovae are used as standard candles because they have a consistent brightness, allowing astronomers to calculate their distances with great accuracy. The teams were attempting to measure the rate at which the universe's expansion was slowing down, as it was expected that the gravitational pull of all matter would gradually decelerate the expansion of the cosmos. But instead, they discovered something completely unexpected: the universe's expansion was not slowing down, it was speeding up. This was a stunning revelation. It meant that some mysterious force was pushing galaxies away from each other at an ever-increasing rate. This force was quickly named dark energy, though the name was merely a placeholder for our ignorance. We did not, and still do not, know what dark energy is. The nature of dark energy. What could dark energy be? Several theories have been proposed, but none are confirmed. Some of the leading explanations include the cosmological constant, lambda. The simplest explanation is that dark energy is a constant energy density filling space homogeneously. This idea actually traces back to Albert Einstein, who introduced a cosmological constant in his equations of general relativity to allow for a static universe. After Hubble's discovery of the expanding universe, Einstein discarded the cosmological constant, calling it his greatest blunder. Yet this same concept has returned as the leading explanation for dark energy. Quintessence. Another possibility is that dark energy is not a constant but rather a dynamic energy field that changes over time. This concept is known as quintessence. Unlike the cosmological constant, quintessence would vary across space and time. Modified gravity. Some physicists have proposed that dark energy is not a substance at all but a sign that our understanding of gravity is incomplete. In this view, the accelerated expansion of the universe might be the result of changes in gravity on the largest scales. Observational evidence for dark energy. The evidence for dark energy comes from multiple sources. Supernova observations. The initial discovery of dark energy was based on type Ia supernovae, but further observations have confirmed this result. Cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, and its detailed study has provided crucial information about the composition of the universe. Observations of the CMB, particularly by the WMAP and Planck satellites, have shown that the universe is composed of approximately 68% dark energy, 27% dark matter, and just 5% ordinary matter. Large-scale structure of the universe. Surveys of galaxies, such as the Sloan Digital Sky Survey, have revealed patterns of structure in the universe that are consistent with the presence of dark energy. The mystery deepens. Despite all the evidence for dark energy, we still have no direct detection or understanding of its true nature. Unlike dark matter, which might be explained by a new type of particle, dark energy could be something far more exotic. It may be a property of space itself, a manifestation of quantum fluctuations, or something we have not yet imagined. Understanding dark energy is one of the greatest challenges in modern physics. It has forced us to confront the possibility that our most fundamental theories are incomplete, and that the true nature of the universe is far stranger than we can currently comprehend. Part 4: Dark Matter versus Dark Energy, Comparing the Unknowns. Dark matter and dark energy are two of the greatest mysteries in modern science, but they are fundamentally different in both nature and behavior. Understanding their distinctions is crucial for grasping their roles in the universe. In this section, we will explore how these two enigmatic concepts differ, their individual effects on the cosmos, and how scientists approach the challenge of studying them. The essential differences. Nature and composition. Dark matter is thought to be a form of matter, albeit one that does not emit, absorb, or reflect light. It is likely composed of a type of particle that we have yet to detect directly. Dark energy, on the other hand, is not matter at all. It is a form of energy, possibly intrinsic to space itself, that exerts a repulsive force causing the universe to expand at an accelerating rate. Role in the universe. Dark matter exerts a gravitational pull, helping to hold galaxies together and influencing the formation of cosmic structures. Without dark matter, galaxies would fly apart due to their rotation speeds. In contrast, dark energy exerts a repulsive force, driving galaxies apart and accelerating the universe's expansion. Proportion of the universe. According to current estimates, dark matter makes up about 27% of the universe's total energy content, while dark energy accounts for roughly 68%. Ordinary matter, everything we can see, from stars to atoms, makes up just 5%. Detection methods. Scientists search for dark matter using underground detectors designed to capture rare interactions between dark matter particles and ordinary matter. They also study its gravitational effects on galaxies and galaxy clusters. Dark energy is studied through its influence on the expansion of the universe, as observed in type Ia supernovae, the cosmic microwave background, and large-scale structure surveys. How dark matter shapes the universe. Dark matter is the cosmic scaffolding on which galaxies and galaxy clusters are built. Through its gravitational pull, dark matter acts as a kind of cosmic glue, binding galaxies together and influencing the way they form and evolve. In simulations of the universe, dark matter is the invisible web on which all visible structures are formed. Dark matter also plays a crucial role in the formation of galaxy clusters. Without the gravitational pull of dark matter, these massive cosmic structures could not exist. Even within individual galaxies, the influence of dark matter is profound. It determines the speed at which stars orbit the galactic center and helps protect galaxies from being torn apart by their own rotation. How dark energy shapes the universe. While dark matter works to hold the universe together, dark energy does the opposite. It drives the accelerated expansion of the universe. Over time, dark energy has become the dominant force in the cosmos, overwhelming the gravitational pull of matter, both dark and ordinary, and pushing galaxies away from each other. This accelerated expansion has profound implications for the future of the universe. If dark energy continues to dominate, the universe may continue to expand forever, becoming increasingly cold, dark, and empty, a scenario known as the Big Freeze. Alternatively, if dark energy is not a constant but a variable force, the future of the universe could take other forms, such as a Big Rip, where galaxies, stars, and even atoms are torn apart. The conflict between dark matter and dark energy. In a sense, dark matter and dark energy are opposing forces. Dark matter works to pull the universe together through gravity, while dark energy pushes it apart. Yet they are not truly in conflict, they are two aspects of the same cosmic puzzle. Understanding both is essential to unlocking the secrets of the universe. The balance between dark matter and dark energy has determined the history of the cosmos, from the formation of the first stars to the current era of accelerated expansion. The ongoing quest for answers. Scientists continue to search for direct evidence of dark matter, using sophisticated detectors buried deep underground, powerful telescopes observing distant galaxies, and the world's most advanced particle colliders. In contrast, the study of dark energy is focused on large-scale astronomical surveys and theoretical work exploring its potential nature. The future of cosmology may depend on our ability to solve these mysteries. As our technology and understanding improve, we may eventually uncover the true nature of dark matter and dark energy, or discover that the universe is even stranger than we can imagine. Part 5: The Cosmic Web and the Role of Dark Matter and Dark Energy. The universe is not a random scattering of galaxies and stars, it is a vast, interconnected structure known as the cosmic web. This web is a massive, three-dimensional network of galaxies, galaxy clusters, and dark matter filaments stretching across billions of light-years. Understanding the cosmic web is crucial to understanding the influence of dark matter and dark energy on the universe. The formation of the cosmic web. The cosmic web began to form soon after the Big Bang, as tiny quantum fluctuations in the early universe were amplified by gravity. Regions with slightly higher density of matter began to attract more matter, while less dense regions were emptied out. Over billions of years, this process led to the formation of massive galaxy clusters, interconnected by filaments of dark matter and separated by vast cosmic voids. Dark matter played a fundamental role in this process. Because dark matter does not interact with light or ordinary matter, it began to collapse under the force of gravity even before the formation of the first atoms. These dark matter clumps became gravitational wells, pulling in gas and dust, which eventually led to the formation of galaxies. Astronomers have mapped the cosmic web using powerful telescopes and computer simulations. The Sloan Digital Sky Survey and the Hubble Space Telescope have provided stunning images of this vast structure. But while we can see the galaxies in the cosmic web, the dark matter that makes up the majority of its mass is invisible. Its presence can only be inferred through its gravitational effects. The role of dark energy in the cosmic web. Dark energy is also a critical player in the evolution of the cosmic web, but its influence is very different from that of dark matter. Whereas dark matter pulls galaxies together, dark energy drives them apart. Over time, dark energy has become the dominant force in the universe, accelerating its expansion and stretching the cosmic web. In the early universe, dark matter was the dominant force, driving the formation of galaxies and clusters. But as the universe expanded, dark energy became increasingly important. It now acts as a kind of anti-gravity, pushing galaxies away from each other and slowing the growth of cosmic structures. Galactic clusters, islands in the cosmic web. Within the cosmic web, galaxy clusters are the largest gravitationally bound structures. These clusters are held together by the gravitational pull of dark matter, which makes up the majority of their mass. Observations of galaxy clusters provide some of the strongest evidence for dark matter. One of the most famous examples is the Bullet cluster, a pair of colliding galaxy clusters. Observations of the Bullet cluster have shown a clear separation between the visible matter, in the form of hot gas, and the dark matter, detected through gravitational lensing. This separation of dark matter from ordinary matter during the collision provides direct evidence of dark matter's existence. Dark energy, by contrast, works to separate galaxy clusters from one another. Over time, as the universe continues to expand, these clusters will become more isolated, and the cosmic web will stretch out even further. The fate of the cosmic web. The future of the cosmic web is a subject of intense scientific study. If dark energy continues to accelerate the expansion of the universe, the cosmic web will eventually become thin and stretched, with galaxy clusters becoming increasingly isolated. This future is known as the Big Freeze, where the universe becomes cold, dark, and empty as galaxies drift beyond each other's reach. An even more dramatic scenario is the Big Rip, in which dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms. In this scenario, the cosmic web itself would be shredded, and the universe would end in a final, catastrophic disintegration. Yet another possibility is a cyclic universe, in which dark energy is not constant but changes over time, causing the universe to oscillate between periods of expansion and contraction. In this scenario, the cosmic web could collapse and reform in an endless cycle. The cosmic web as a laboratory. Scientists study the cosmic web not only to understand dark matter and dark energy but also to test fundamental theories of physics. The distribution of galaxies in the web can reveal clues about the nature of gravity, the properties of dark matter, and the behavior of dark energy. By comparing observations of the cosmic web with computer simulations, astronomers can test their understanding of how the universe works. Any discrepancies between the observed and simulated cosmic web could point to new physics. Part 6: Dark Matter Detection, the Search for the Invisible. Despite its profound influence on the universe, dark matter remains elusive. Unlike ordinary matter, it does not emit, absorb, or reflect light, making it invisible to telescopes. Yet scientists are determined to uncover its nature, using a variety of methods that probe the dark matter mystery from multiple angles. Direct detection, the quest for dark matter particles. One of the primary methods for detecting dark matter is through direct detection experiments. These experiments are typically conducted deep underground, where they are shielded from cosmic rays and other forms of background radiation that could interfere with their results. One of the most well-known direct detection experiments is the Large Underground Xenon (LUX) experiment, which uses a tank of liquid xenon to detect potential interactions between dark matter particles and atomic nuclei. If a dark matter particle collides with a xenon nucleus, it should produce a faint flash of light, which can be detected by sensitive sensors. Other experiments, such as Xenon LUX Zeppelin, are designed to improve on the sensitivity of earlier efforts, pushing the limits of what we can detect. These underground experiments are based on the assumption that dark matter particles are weakly interacting massive particles, WIMPs, a popular theoretical candidate for dark matter. Indirect detection, searching for dark matter's signature. Another approach to finding dark matter is indirect detection, which involves looking for the byproducts of dark matter interactions. According to some theories, dark matter particles can annihilate each other, producing high-energy particles such as gamma rays, neutrinos, or even antimatter. Astronomers use space-based observatories like the Fermi Gamma Ray Space Telescope to search for gamma rays that may be produced by dark matter annihilation in regions of space with high concentrations of dark matter, such as the center of our galaxy or dwarf galaxies orbiting the Milky Way. Ground-based observatories, such as the Ice Cube Neutrino Observatory in Antarctica, look for high-energy neutrinos that could also be produced by dark matter interactions. By analyzing the direction and energy of these neutrinos, scientists can determine whether they may have originated from dark matter. Collider experiments, creating dark matter. Another approach is to try to create dark matter directly in a laboratory setting, using particle accelerators like the Large Hadron Collider, LHC, at CERN. The LHC smashes protons together at incredibly high energies, recreating the extreme conditions of the early universe. If dark matter particles can be produced in these collisions, they should leave a signature of missing energy, a gap in the energy and momentum of the particles produced in the collision. By carefully analyzing these collisions, scientists hope to uncover evidence of dark matter. Collider experiments are particularly useful because they allow scientists to test specific theories about what dark matter might be. If a new particle is discovered that matches the properties of a proposed dark matter candidate, it could revolutionize our understanding of the universe. Gravitational detection, the lensing effect. Although dark matter cannot be seen directly, its gravitational effects can be observed. One of the most powerful techniques for studying dark matter is gravitational lensing, which occurs when the gravity of a massive object, such as a galaxy cluster, bends the light from objects behind it. Gravitational lensing can be used to map the distribution of dark matter in the universe. By analyzing the distorted images of distant galaxies, scientists can determine where dark matter is located, even though it is invisible. This technique has been used to create detailed maps of dark matter in galaxy clusters, revealing a vast, invisible network of dark matter filaments. The hunt continues. Despite decades of effort, scientists have yet to directly detect dark matter particles. But the search is far from over. New experiments are being developed, and existing ones are constantly being upgraded to increase their sensitivity. The nature of dark matter is one of the most profound mysteries in science, and its discovery would open a new chapter in our understanding of the universe. Whether it is a new type of particle, a modification of our understanding of gravity, or something even more exotic, the answer to the dark matter mystery will reshape our view of the cosmos. Part 7: Dark Energy Detection, Deciphering the Force of Expansion. Dark energy is an even greater enigma than dark matter. While dark matter can be inferred through its gravitational effects on galaxies, dark energy is known only through its influence on the expansion of the universe. Understanding dark energy is one of the most profound challenges in modern science, and researchers use a range of techniques to study this mysterious force. Supernova observations, the accelerating universe. The discovery of dark energy was a profound shock to the scientific community. In 1998, two independent teams of astronomers used observations of Type Ia supernovae to measure the expansion rate of the universe. These supernovae, which are stellar explosions that occur under specific conditions, have a consistent brightness that makes them standard candles for measuring cosmic distances. To the surprise of scientists, the supernovae appeared dimmer than expected, suggesting that they were farther away than their redshift indicated. This observation meant that the universe's expansion was not slowing down due to gravity, as expected, but was instead accelerating. This acceleration could only be explained by the existence of a new form of energy, dark energy, pushing the universe apart. The cosmic microwave background, tracing the early universe. Another powerful tool for studying dark energy is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. By studying tiny fluctuations in the temperature of the CMB, scientists can learn about the universe's composition and its rate of expansion over time. The Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided precise measurements of the CMB, allowing scientists to determine that dark energy makes up about 68% of the universe. These observations have also revealed that dark energy has a constant energy density, at least so far, which is consistent with the idea of a cosmological constant, first proposed by Albert Einstein. Baryon acoustic oscillations, mapping the universe's growth. Baryon acoustic oscillations, BAOs, are another technique for measuring dark energy. These are subtle patterns in the distribution of galaxies across the universe, which were imprinted by sound waves traveling through the hot, dense plasma of the early universe. By measuring the size of these patterns at different distances, scientists can track how the universe's expansion rate has changed over time. This technique has been used in large-scale galaxy surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, to map the influence of dark energy over billions of years. The Hubble constant controversy. The study of dark energy has also led to a significant controversy in modern cosmology, the Hubble constant crisis. The Hubble constant is a measure of the universe's expansion rate, but different methods of measuring it have produced conflicting results. One method, based on observations of the CMB, produces a lower value for the Hubble constant, while another method, based on supernova observations, produces a higher value. This discrepancy could indicate that our understanding of dark energy, or even the fundamental laws of physics, is incomplete. Dark energy models, theories beyond the cosmological constant. While the simplest explanation for dark energy is a cosmological constant, an inherent energy of space itself, other models have been proposed. These include quintessence, a dynamic form of dark energy that can change over time, rather than remaining constant. Phantom energy, a form of dark energy that becomes stronger over time, potentially leading to a Big Rip scenario where the universe is torn apart. Modified gravity, an alternative idea that suggests dark energy is not a form of energy at all, but rather a result of a modification to our understanding of gravity. Scientists continue to test these models using observations of the universe's expansion, the distribution of galaxies, and the behavior of the cosmic web. The future of dark energy research. New observatories, such as the Vera C. Rubin Observatory, the Euclid mission, and the Nancy Grace Roman Space Telescope, are being developed to study dark energy with unprecedented precision. These observatories will map billions of galaxies, measure the growth of cosmic structures, and search for new clues to the nature of dark energy. Dark energy may be the most mysterious force in the universe, but it is also one of the most important. Understanding dark energy is essential to understanding the universe's past, present, and future. Part 8: Theoretical Models of Dark Matter and Dark Energy. While dark matter and dark energy are both essential to our understanding of the universe, their true nature remains a profound mystery. To solve this puzzle, scientists have proposed numerous theoretical models, each attempting to explain the properties of these elusive phenomena. Cold dark matter versus warm and hot dark matter. One of the most important distinctions in dark matter theories is the temperature of dark matter particles. The most popular model is cold dark matter, CDM, which consists of slow-moving particles that cluster together to form the large-scale structures we see in the universe. This model is favored because it accurately predicts the formation of galaxies and galaxy clusters. However, other models propose that dark matter may be warm or hot. Warm dark matter consists of particles that move at moderate speeds, while hot dark matter is made of particles that move at nearly the speed of light. These models are less favored because they struggle to explain the observed distribution of galaxies. WIMPs and axions, leading candidates for dark matter. One of the most popular theories is that dark matter is made up of weakly interacting massive particles, WIMPs. These particles are predicted by extensions of the standard model of particle physics, such as supersymmetry. WIMPs are thought to interact with ordinary matter only through gravity and the weak nuclear force, making them extremely difficult to detect. Another leading candidate is the axion, a hypothetical particle that was originally proposed to solve a different problem in particle physics. Axions are extremely light and interact very weakly with matter, but they could exist in vast quantities throughout the universe, providing the necessary dark matter. Modified gravity. An alternative to dark matter. While most scientists believe that dark matter is a new type of particle, some have proposed that it may not exist at all. Instead, they suggest that our understanding of gravity is incomplete. These theories are known as modified gravity theories. One of the most well-known modified gravity theories is modified Newtonian dynamics, which suggests that gravity behaves differently at extremely low accelerations. Another is TeVS, tensor vector scalar gravity, which is a more advanced version of MOND that attempts to provide a complete description of gravity without the need for dark matter. Dark energy, theories beyond the cosmological constant. The simplest explanation for dark energy is that it is a cosmological constant, an inherent energy of empty space. This idea is consistent with observations, but it raises profound questions. Why does dark energy exist at all? Why does it have the strength it does? To answer these questions, scientists have proposed more complex theories. One of these is quintessence, which suggests that dark energy is a dynamic field that can change over time. Another is phantom energy, which predicts that dark energy will become stronger over time, eventually tearing apart galaxies, stars, and even atoms in a Big Rip scenario. The holographic principle, a radical possibility. One of the most exotic ideas is the holographic principle, which suggests that our three-dimensional universe is actually a projection of information stored on a two-dimensional surface. This idea, which is rooted in the physics of black holes, could provide a new way to understand both dark matter and dark energy. In this view, dark matter and dark energy may be the result of information encoded on this two-dimensional surface, which influences the behavior of our universe. Testing theories. The role of observations and experiments. Theories are only as strong as their ability to make accurate predictions. Astronomers and physicists continue to test these ideas using a wide range of techniques, from underground dark matter detectors to space-based observatories. As technology advances, new data may support one of these theories or force scientists to develop entirely new ideas. But even if dark matter and dark energy remain mysterious, the search for their true nature is driving profound advances in our understanding of the universe. Part 9. The role of dark matter and dark energy in cosmic evolution. Dark matter and dark energy are not just passive components of the universe. They play active, dynamic roles in shaping the cosmos, influencing everything from the formation of galaxies to the ultimate fate of the universe. Understanding these roles is essential to understanding the history and destiny of the universe itself. Dark matter, sculptor of galaxies. Dark matter is often described as the scaffolding of the universe. Shortly after the Big Bang, the universe was a nearly uniform sea of hot, dense plasma. But tiny fluctuations in this plasma, amplified by the gravitational pull of dark matter, created regions of higher density that eventually collapsed to form the first galaxies. Without dark matter, galaxies as we know them could not exist. Ordinary matter, which interacts through electromagnetic forces, is subject to processes like radiation pressure and turbulence that prevent it from collapsing quickly. But dark matter, which interacts only through gravity, can form dense structures much more easily. These structures serve as the gravitational wells in which ordinary matter gathers to form galaxies and stars. Simulations of cosmic evolution, such as the Illustris and Eagle projects, have shown that including dark matter is essential to producing realistic galaxies. These simulations reveal a vast, cosmic web of dark matter filaments, with galaxies forming at the intersections of these filaments. Dark energy, the driver of cosmic expansion. While dark matter pulls galaxies together, dark energy pushes them apart. After the Big Bang, the universe's expansion was initially slowed by the gravitational pull of dark matter and ordinary matter. But around 5 billion years ago, dark energy became the dominant force, causing the expansion to accelerate. This accelerating expansion has profound consequences for the future of the universe. If dark energy remains constant in strength, the universe will continue to expand forever, with galaxies drifting farther and farther apart. If dark energy increases over time, it could lead to a Big Rip, where galaxies, stars, planets, and even atoms are torn apart. On the other hand, if dark energy eventually decreases or reverses, the universe could enter a big crunch, collapsing back in on itself. These scenarios are not just theoretical, they depend on the true nature of dark energy, which scientists are still trying to understand. The balance of dark matter and dark energy. One of the most profound questions in cosmology is why the universe contains the particular balance of dark matter and dark energy that we observe. Dark matter makes up about 27% of the universe, while dark energy makes up about 68%. Ordinary matter, which makes up everything we can see, accounts for just 5%. This balance is not just a coincidence, it determines the universe's structure, its expansion history, and its ultimate fate. A universe with too much dark matter would have collapsed into black holes long ago. A universe with too much dark energy would have expanded too quickly for galaxies to form. This delicate balance is known as the cosmic coincidence problem, and it is one of the great unsolved mysteries of cosmology. Some scientists have proposed that it may be the result of a deeper principle, such as the anthropic principle, which suggests that we observe this balance because only a universe with this balance could produce observers like ourselves. The evolution of cosmic structures. The interaction between dark matter and dark energy has shaped the evolution of the universe on every scale, from the formation of individual galaxies to the growth of galaxy clusters and superclusters. In the early universe, dark matter dominated, allowing galaxies to form. But as dark energy became more powerful, it began to pull these galaxies apart. Today, most galaxies are drifting away from each other, with the expansion of the universe accelerating. This process has created a universe that is both dynamic and ever-changing. It has also given scientists a powerful tool for studying dark matter and dark energy. By observing how the universe has evolved over time, they can test their theories and refine their models. Conclusion. Dark matter and dark energy are the greatest enigmas of modern cosmology. They are invisible forces that shape the universe, guiding the formation of galaxies, determining the fate of the cosmos, and challenging our deepest understanding of physics. For centuries, humanity has sought to understand the nature of reality, from the orbits of planets to the behavior of subatomic particles. Yet, even after centuries of exploration, the universe has revealed that most of its substance is hidden from view, operating beyond the reach of our senses and our instruments. Dark matter, the unseen structure that holds galaxies together, and dark energy, the mysterious force driving cosmic expansion, are reminders of our limitations and our potential. They are the frontiers of discovery, pushing scientists to develop new theories, build more advanced instruments, and explore the universe on the grandest scales. But they are also a source of wonder. They show that the universe is not a static, predictable machine, but a vast, dynamic, and mysterious realm, filled with phenomena beyond our imagination. As we continue to probe the darkness, we are not just uncovering the secrets of the universe. We are expanding the boundaries of human knowledge. And perhaps one day, we will finally understand the true nature of dark matter and dark energy, completing the picture of our cosmic story.